Anybody have any homework questions before I start with the new stuff? Yep. Number 4. Can I see that from someone? Number 4 in the matrices.
I have that shirt. I got it for my birthday. That same Iron Man shirt.
I look super handsome in it because of my physique. About my physique? Oh. I think you and my answers differ on that. Okay, so matrix math number 4. So A is 1, 0, 3, minus 5, 5, 2. And B is 4, 1, 3, negative 7, 2, negative 9. And it asks for sizes and stuff. The size of A, there are 3 rows and 2 columns, so that's 3 by 2. B has 2 rows and 3 columns, so that's 2 by 3. A1, 2, that is the first row, second column, so that's 0. B2, 1 is the second row, first column, so that's negative 7. And then AB, or which can you calculate, AB or BA? Well, you can do either one of those. AB, so because that's a you're multiplying a 3 by 2 and a 2 by 3, and those match. Yeah, so the yeah. So 2 by 3 times 3 by 2 is calculable because those match. And by the way, you can... What? That's B times A, yeah. By the way, I don't know that this is ever going to come up in this class, but matrix multiplication. Can be written with summation notation. So if you have, if you're multiplying a matrix A times matrix B, you can think of that as A, let's say MI times BIN, as I goes from 1 to, whatever the number of that element is. And so if you're ever writing a matrix, that won't come up anytime super soon, but whenever you are writing matrix multiplication into computer programs, it's pretty easy to do with this way of thinking about it. Anyways, it's using the same fact as this. Any other homework questions?
So it's not a homework question, but looking back at the two that match, how are you able to tell what size of matrix?
Then the matrix that comes out is going to be, in this case, 3 by 3, and in this case, 2 by 2. The outside. The insides have to match, and the outsides give you the dimensions of the new matrix. Yeah. Yes. Nope. Doesn't have to match. Just the inside has to match. Yep. We're not going to have, like I mentioned before, all our matrices are going to be of a few types. All our multiplications are going to be the same size as a matrix over and over again. So you won't have to think about that stuff too much. But anything else right now? Okay, so today let's define. We'll start with the definition of the stress tensor, the most important thing in this class, and then I think we'll also go into the definition of the strain, the state of strain, the second most important thing in this class, and we'll be pretty much done. Just drink lemonade and whatnot. Okay, so the stress tensor. This is a measure of internal loads at a material point. And it's the single best predictor of whether a material is going to fail at a point. You can come up with some balance by combining stress and strain in certain ways, but if you had to just come up with one physical quantity that you were going to use to predict whether something was going to break or not, this is the one you would use. And so here's the idea. This is at a single material point. I mentioned that last time. So internal loads, like we did in statics, if you're talking about the internal loads in a beam, that tells you along a line the total loading applied to one side by the other side. So that's not at a point, although we kind of talked about it that way in statics. It's actually along a surface. you can imagine there's a surface area of contact between the left side and the right side of this beam. And so what we want to do with stresses is we want to figure out the loading is acting on a single point on that surface, not the whole surface. So what we're going to do, thinking about this, is we're going to isolate a cube of material that's centered at the location we care about. For now, it's finite. So imagine a finite cube of material centered at the desired point. And then we're going to do a limiting procedure to go from the loads on this finite cube to the loading that's happening on this infinitesimal cube with the same center. So let me draw this cube. Okay, so here's the material. And inside this material, we have this finite cube. And I'll draw a blown up version of that. So what kind of loading is happening on that cube? Well, using the same reasoning that we did with internal loads in statics, each one of those faces is connected to the surrounding material by a fixed joint, right? It's all the same material. And so what we expect is a full force vector and a full vector of couples that's applied to each one of these faces by the surrounding material. Okay, so we have the force vector and the couple. There. And there. And there. Those are the only three we can see the way I drew it here, but same thing's going on the three obscured faces. So right now, total values that define the internal loads on this cube. We have 3 components of force on each face and 3 components of couple on each face. So that's 6 total values defining each face. There's 6 faces on a cube, so we're talking about 36 total values defining the state of loading on that cube. Okay. Couples. So the internal loading on this finite cube, I'm saying finite cube to differentiate between this and then the final thing we're going to get when we take a limit and this thing gets down to an infinitesimal size. So right now we have 18 force values and 18 couple values. And you would think, I mean, just off the top of your head, you would think like, okay, we're going to take these limits and then these 36 total values in the limit are going to define our loading. But when you take, so now let me say the idea is to find the limits of these 36 values as the cube size approaches 0. We're going to have to modify things a little bit, though, because as the cube size goes to 0, those forces, and therefore the couples, also approach 0. So all 36 values also approach 0 as the cube size approaches 0. And I mean, there'd be some benefits to having the stress of any material point being a matrix of 36 values of 0, easy to calculate. The problem is it doesn't tell you anything, So to fix that, instead of thinking of these as 36 values of force and torque, we'll use 18 values of force per area and 18 values of torque per area. Well, torque per area still goes to 0 as you take that limit. And the reason for that is that even though force per area now isn't going to approach 0, you multiply that by the distance those two forces are acting apart to get the couple. And as you shrink the size down, that moment arm is going to 0. Okay, and so forget those. Those couples are not going to come into this at all. But those are going to be non-zero, and that's going to define the stress tensor. Because the force is also going to 0. One of them, they're indeterminate forms. Is that what they call those? The limit of 0 over 0? Yeah. Yes. Because remember, the couple is the force times a moment arm distance between the two forces. The couple is two equal and opposite forces at a distance. And that distance comes into the calculation. So even if the forces are finite, if you're shrinking the distance between the two forces, it goes to 0. But yeah, force per area approaches finite values. So the stress at a material point is made up of 18 force per area values as the cube size approaches 0. Okay, and we're going to represent this on a cube graphically. This cube that I'm drawing is infinitesimal. But we're going to represent this on a stress cube, it's called. Actually, I don't know if it's called that or if I just call it that. It's infinitesimal, so it's not drawn to scale. And so on every one of the faces, you have a value in the x direction, a value in the y direction, and a value in the z direction. I'm going to name these sigma xx. The vertical one here is sigma xy. This one's sigma xz. And now going to the front face. And one thing to notice about this notation is that the first subscript tells you what face you're on. Here we're on the face that the x-axis pokes through. And the second subscript tells you which component of that force per area vector. Now, so the front face would be the z face. My coordinate system is like this. X, Y, Z. Okay. Right. Well, yeah, because this is the component in the x direction, in the y direction, the z direction, and this is the face that the x-axis points out of. That's why the first subscript. So, okay, the second one, this is the positive z face, because the z-axis, the positive z-axis is pointing out of it. And so here we have sigma z x, sigma z y, and sigma z z. And now up here, this is the positive y face. So we have the component sigma yx, sigma yy, and sigma yz. So that's 9 values. There are 18 total because I didn't draw it on the opposites, but the face that's over here, right here, opposite this one, is called the negative x face because the x-axis is pointing into that face. The positive ones are with the axis pointing out of it. Underneath is the negative y face, and straightened back is the negative z face. Okay, and those are also there. So the first subscript is the face. The second subscript is the component of the traction on that face. That's not annoying, don't worry. Okay, so on the x face, on the positive x face, the traction is made up of these three components of force per area. On the z face, these are the components of the traction. And on the y face, those are the three components of the traction, and those are vectors. So traction on each face is a vector. All right, so 18 values. It turns out that only some of those are necessary for describing the stress, and we can figure that out from analyzing the physics of it. So not all of these 18 traction values needed to define the stress. So the first analysis says is based on Newton's second law. And Newton's second law, if you go through the analysis and require that this is in static equilibrium, so if the object is in static equilibrium, not accelerating, tractions on negative faces have to be equal and opposite to the tractions on the positive faces. So if I know the traction values here, it's redundant to tell you what the values are over here. Those just always have to be equal and opposite to these. There's no other way to keep this from accelerating. Okay. That's not super obvious at first glance, but if you went through Newton's second law for all this, that's the only way you could do it. And so now we don't have 18 we don't have 18 useful values to define the stress anymore. We're down to 9. We've cut half of them out because half are on the negative faces. Any questions so far? No, we're going to do it all in 3D. It is all going to be 3D. Mm-hmm.
So we just since the x phase we explain, but we're going up y up z, we don't go like the component like x y.
Yeah, we do. Like on the x phase, on each phase there are 3 components, 3 vector components.
Oh, on each phase. Oh.
Yeah.
So the phase only there's one on the x, one on the y,
and one on the z. And now what I just said was that the negatives don't matter, so we're only worried about the positive faces. And we're trying to cut this down to as little information as possible. 36 values is a lot to track around for a single. So, and little by little, we're cutting it down to the information we need. So Newton's second law says don't have to worry about the negative faces. Now the moment equation, rotational Newton's second law, says that if the object is in static equilibrium, yeah. So even if you're doing these kind of calculations for an object that's not static, you can assume that it is, because we're going to be dealing with really big stresses, and the contributions that would be made by accelerations would be tiny compared to the ones produced by the loads. I mean, just imagine, so we're talking about the kind of forces that'll rip steel apart. You know, that's what we're trying to calculate. Imagine how fast you'd have to spin something to make spin a steel object to make it rip apart. You've never seen such a thing happen, and so it's just not going to be an issue. You know what I mean? So if an object's in static equilibrium, the AB traction has to be equal to the BA traction. So let me show you what that means. So to keep this thing from spinning, this value has to be equal to this value, and this value has to be equal to this value, and this value has to be equal to this value. Okay, so yeah, right, yep. If that was not the case, then this thing would spin, and there's no other way for it to work out. So what that says is we don't have 9 values anymore. We're down to 6. And so these 6 independent values can be represented by a symmetric 3x3 matrix. And this 3x3 matrix is called the stress tensor. A tensor, you probably haven't heard that word before, or you haven't dealt with it much before, but the same way I think I mentioned sort of in passing last class that a vector isn't just a column vector, although like a vector is a column vector, but not all not a vector is a column matrix, but not all column matrices are vectors. To be a vector, you have to have this property that applying rotation matrices to it, rotating the coordinate system, doesn't change the meaning of the vector in some way. And a tensor is like a square matrix. It can be any size that sort of has the same meaning. All tensors are square matrices, but not all square matrices are tensors. To be a tensor, you have to have some kind of invariance of meaning as you go from one coordinate system to another. Okay, and so the final stress tensor, which we're going to write as the Greek letter sigma under squiggle, and the elements are sigma xx, sigma xy, sigma xz. And now I'm going to take advantage of the symmetry of this matrix and call this next element, like you would think it would be sigma yx, but I'm going to write it xy again because these have to be equal. And sigma yy, and sigma yz. And then again, I'm going to use the symmetry twice, so we have sigma xz, sigma yz, and sigma zz. That's the stress tensor, the most important thing in this class. The SI units for stress are newtons per meter squared. And that's given its own name, the Pascal, or capital P lowercase a. And since we're going to be talking about really big values in pascals, we're talking about the values that can, cause metal objects to fail. Often you'll see these mentioned as megapascals or gigapascals. To pressure. Yes, it's the same units as pressure, and sometimes it is similar, yeah. Sometimes they're kind of interchangeable. Well, we could have chosen any shape, but it would have been much more tricky to do the geometry if we'd chosen a sphere or something, so we just chose something where the geometry would be simple. The diagonal elements of the stress tensor called the normal stresses. And the off-diagonal elements are called shear stresses. Okay, so let's just look back at where these values are on the cube. So the diagonal elements are all the ones with matching subscripts, XX, YY, and ZZ. So those diagonal elements in the stress tensor are the vector pointing normal to the X face, normal to the Y face, and normal to the Z face. So that's why those are called the normal stresses. Those are equivalent to telling you the compression or tension at a point. And then all the off-diagonal elements are the ones that are running parallel to the face that they're on. If you imagine what scissors do, shears, to a piece of material, they cause loading like that. And so that's why those are called the shear stresses. When you cut something, you cause big shear stresses in the material. Okay, so let's, one of the first things we need to do is get comfortable taking the stress tensor and drawing it and imagining it as a stress element so we can just picture what's going on. So for example, let's say we have the stress tensor negative 10 times 10 to the 6, negative 5 times 10 to the 6, 0. What does this value have to be? Negative 5, yep. The diagonals can always be, they're always independent. So that can be 0. Say this one's negative 2 times 10 to the 6. That shouldn't have been negative 6. That should be where I am here. That should be to the positive 6, 10 to the positive 6. And then the last row, we have 0 due to symmetry. Negative 2 times 10 to the 6, and then 0. And all of these elements have units of pascals. And we just want to draw the stress element representing this state of stress. Okay, so There's the cube. The XX stress, the stress that's normal, the traction component that's normal to the positive x face is negative 10 times 10 to the 6th. Positive would be out of the face, so this is 10 times 10 to the 6 pointing into the face. Then on the x face in the y direction, we have negative 5 times 10 to the 6th. So that's a component in the negative y direction. So that's down with a value of 5 times 10 to the 6th. And then on the x face, nothing in the z direction. And now we'll go to the y face. On the y face, in the x direction, we have negative 5 times 10 to the 6th. So that means we have 5 times 10 to the 6 in the negative x direction. We have nothing in the y direction. And then in the negative z direction, we have 2 times 10 to the 6. And then on the z face, we have nothing in the x direction. In the y direction, negative y direction, we have 2 times 10 to the 6. And nothing in the z direction. This obscured face over here has all the equal and opposite values to this one. And so we know from looking at it, it's a little hard to visualize how you develop these loads. But one thing that's easy to imagine is what those normal stresses are doing. So if we're pushing this way on the positive x face, it means we're pushing this way on the negative x face. And so we're compressing it like this. Okay, that's what those normal stresses tell you. And if you have positive values of the normal stresses, it means you're stretching it. Yes?
So the face X, Y, and Z are the row, right? So
What?
the row or
Yeah, every row is the traction components on a face. Yep. Yep.
Go down the elements in terms of the faces. So the second row was it sigma xy or sigma yx?
We'll write it sigma xy because I said that if you analyze the physics, you see that they have to match. So we'll just always write those the same.
But the second row is on the y face.
Yeah,
And then
that's right. That's right. So the first row is on the x face, second row is on the y face, third row is on the z face. But when we write them, we enforce the symmetry by the way we order those subscripts. Yep. The components of the traction go across the row. Yep. A positive value always points in the direction of the positive axis. That's the easiest way to think about it. So like in this example, the XX normal stress was negative. So on the X face, that had to be pointing in the negative X direction. And that's assuming a coordinate system like this. Okay, 5 minutes. Let me say one more thing. There's a very important relationship between the stress tensor and tractions on a face. let's say on a chosen face. If n hat is the unit normal vector pointing out of a face, then the stress tensor times that unit normal is equal to the traction vector on that face. So where t is the traction vector on that face. It's easy to see that if you think about the faces of the stress cube itself. So with the faces of the stress cube, so like for example, the traction on the negative x face. Well, let's do positive first. On the positive x face, so here's our general stress tensor. Okay, and so now we want the outward facing normal vector to the positive x face. One that's going from inside the material to outside the material. That's just going to be 1, 0, 0. And if you do that multiplication, you get sigma xx, sigma xy, sigma xz. Just like, we know that that's the traction on the positive x face. So let's do one on a negative face. So let's say negative y face. So I'll take this stress tensor. And on the negative y face, what's the outward facing, what's a unit vector that faces outward to the negative y face? 0, negative 1, 0. Yep. We'll go 0, negative 1, 0. And if you do that matrix multiplication, you get negative sigma x y, negative sigma y y, negative sigma y z. And if you look up at the, if you draw just a normal stress element, a normal stress cube, on the positive y face, you have sigma x y, sigma y y, sigma y z. We know on the negative face it has to be equal and opposite. So this tells you what the traction vector is on the negative face. In fact, I'll finish this next time, but This also works on faces that aren't lined up with the faces of the cube. And so, like, if you have a material like this, and you're trying to figure out what you know about the tractions on the face, let's say this is 45 degrees, you can use a normal vector, an outward-facing normal vector, like that. So this n would be 0.7071, 0.70710. Multiply that by the stress tensor, and it would tell you what the traction has to be on this face. Often you use it, and I'll do an example of this, but usually measuring that traction on a face like this is the easy part, and you're trying to measure the stress. And so you use this requirement in reverse to figure out what you know about the stress values at the boundaries. I'll do an example of that. Any questions? Okay. I'll get the assignment up as soon as I can.